thermodynamics. So if you say the definitions, what we are doing here, you can say that study of flow of heat or any form of energy into or out of systems which undergoes a physical or chemical transformation. So thermodynamics we can define as the study of flow of heat or any form of energy so into or out of systems, and it helps to physical or chemical transformations. So in thermodynamics we are mainly studying the flow of heat or any form of energy. So before you start the thermodynamics, we should know some terminology, like some terms which we are using in these chapters repeatedly. So terminology or terms of these chapters are: first is system. What are the system? System is the part of the universe which is under thermodynamic study. Or part of the universe which is interested or which is part of investigations. So part which is thermodynamic study or part of investigations or part of observance. Part of in observance. So these are that part of the universe which we are actually interested, which we are studying. So that part of universe we are called as systems. And for universe, and for surroundings, what is surroundings? So except systems, other parts of universe is called surroundings. So except systems, remaining part of universe it's called surrounding. So if you leave the systems, then whatever the remaining parts, that all called as the surrounding of that systems. So next terminology you will look, that is boundary. So what is boundary? It is the imaginary. So this can be real or imaginary surface which separate the system from surrounding. So that surface which separate the systems from surrounding, so that surface is called boundary. And this boundary this boundary can be real boundary or can be imaginary boundary. So let's search this in the open systems. So this is system. Suppose this is water. So in the water, so this water is system. So surrounding is other than other part of the other than systems, the remaining part of the universe is called surrounding. Means this is systems. Then other than these systems, all are surrounding. So this is surrounding. This is surrounding. So this is surrounding. So all except systems, other part. So that surrounding is that part of the universe which is all except systems. Except system, everything is surrounding. So these all are surrounding. So this system and surrounding is separated by here. There is no real boundary is not present. But here from this surrounding and this system, there is a boundary. This uh, this glass. So suppose this is a beaker. So this beaker, suppose this is made by some maybe steel or something. So this is a real boundary. So this is a real separation between this system and surrounding. So this is a real boundary. And from here, this is surrounding, this is system, and these are separated, but there is no any real boundaries there. So this is imaginary boundary. So boundary can be real or imaginary. And boundary can be adiabatic or can be diathermic. Can be adiabatic or can be conductive boundary, or this one we can say that diathermic boundary. So how can you say? Suppose this is a closed vessels and water is there. And if you are giving heat, so if this is a conducting wall, so this wall is a, suppose this wall is conducting wall, means heat transfer can occur. Heat transfer can occur. So for conducting wall, heat transfer can occur. So this heat will be transferred to this water, and this water get heated it, and it will go evaporated. So here, so here, so this is a this boundary is called conducting boundary. And another type of boundary is, suppose here water is there, and again if we are giving the heat, but this is adiabatic boundary. Adiabatic boundary means, or insulating wall, means no heat can transfer. So for this case, what happened if we heat, then also this water will not get heated because heat is not transferring, so this wall is not allowing the heat to transfer. So this is a type of adiabatic boundary, so where heat is not transferred. So the boundaries can be real or imaginary, can be adiabatic or can be conductive boundary. So next we will study the type of systems. So we have studied that what is a system. System is a that part of the universe which is under thermodynamic study or which is under investigations. So systems can be three types. One is open system, another is closed systems, another can be isolated system. So what are open systems? Open systems, this is the system which allow the transfer of both matter and form of energy, that can be heat or work, from its surroundings. What it says, the systems which allows the transfer of both matter and energy from its surroundings. So both matter and energy can transfer between system and surroundings. Then that type of system is called open systems. How can you say? Example, you can say, suppose water is here and suppose you give the heat, then what happened? This is open. So this is open system. What if he give the heat, then this water get heated, and this is conducting wall. This wall is conducting wall. So if you give the heat, so since this is conducting wall, so it allows the heat to transfer. So this heat can enter into the systems, and the systems, that is water is present here in the system, water is there, so this water get heated in this way and this will get evaporated, and water will go out from this system. So what happening here, that matter exchange. So matter exchange is happening because the water is getting lost, because water is getting evaporated, means water is the amount of water is decreasing, so matter exchange is happening. So mass of the system is decreasing, means matter is decreasing, so mass exchange is happening. So mass exchange is happening due to mass exchange occurring due to open system. Yes, and this is one. And secondly, or I can write here, second word, that heat is transferring, means energy transfer also occur. So energy exchange, so energy exchange also happening. So energy exchange happening due to, so happening due to due to this conducting wall. So both matter exchange and energy exchange is happening. So for open systems, both matter and energy exchange can occur. And second type of system is closed systems. So closed systems is systems which do not allow the transfer of matter, but allow the transfer of energy from its surrounding is called closed system. Is called closed systems. So a closed system is a system where it do not allow the transfer of matter but allow the transfer of energy. So closed systems where matter will not transfer but energy will transfer, and these closed systems can be two types. One is two types we can explain. A types is where heat exchange occur. So this is let's say here water is there, and if we give the heat rate, and this is conducting wall, and this is closed system. So it is closed system. So here what happened, that matter, I can write here, matter exchange. So no matter exchange, due to closed systems, but energy exchange. So since this is a conducting wall, so this heat can transport to these systems. So water get heated because this is a conducting wall. So heat exchange occur due to conducting wall. So another type is work exchange occur. How? So suppose I take the same, this is suppose water is there, and it is pistons. If we give, then what happened, like so suppose this amount of is there, and if you remove the balls, then it will shift, or you can say if I add more number of balls, then what happens? This water level will decrease. So this volume is decreasing, and so if volume, we know that pressure is indirect proportional to volume. So if volume is decreasing, then pressure is increasing. So here PB work is occurring. So work is occur here. So for this matter exchange no, due to closed systems. So matter will not exchange because this is a closed, so matter cannot transfer. So matter exchange no due to closed systems. Another is energy exchange. So energy exchange occur due to work exchange. So this type of pistons we will study in reversible reactions or in further. So this is just for giving you the examples where the closed systems where energy exchange can occur due to work exchange. Another way, the energy exchange occur due to heat. So here this wall is adiabatic wall, or by I said this is insulating wall. So heat will not transfer here. So heat is not transfer. Then we can do another way the work energy exchange by doing the piston shifting. So by piston shifting the work will occur. So if work occur, then energy exchange occur, because energy exchange can occur by two ways, either by changing heat or changing or doing work. So in the first case, by exchanging heat we did the work, energy exchange occurs. And the second by shifting the pistons, the work exchanges occur. So work has done, so energy exchanges occur. So closed systems we can explain by two ways. If the wall is insulating, then on that case work exchange piston is there, then also it is a closed systems. And if the wall is conducting wall, then heat exchange occurs, and it is a closed system, then also energy is exchanging due to this is a conducting wall, so heat transfer is occurring. So third types, that is isolated systems. So isolated systems, a system which do not allow both matter and energy exchange, which do not allow matter and energy exchange or transfer from its surrounding. So if I say this, the wall, and this is closed systems, and this water is there, and at the same times this is insulating wall. So if it is insulating wall and it is a closed system, so either we cannot change the matter, we cannot exchange the matter because this is a closed system, and energy transfer is also not possible because it's insulating wall. and if it may given the piston, then we can do another exchange by doing work, but piston also not there. So for this, no matter or no energy can exchange. So this is a type of isolated systems. So next we will study that property thermodynamics. This is properties because this is applicable for all. So first is extensive properties. What are the extensive properties? The properties the properties which do not which depend the quantity of matter present in the system. So extensive property is the property which depends the quantity of a matter present in the system. So it depends the quantity of matter present in the system. So that property is known as extensive properties. So if I say the examples like volume, and we can say extensive properties, so which depends on the quantity of matters. So you can say enthalpy, we will study after some times, gives free energy, and internal energy. These are extensive properties. It depends on the quantity of matter. So like if I say this is bucket of water is here, so let's say I will take this amount of water from here by mug. So this is mug. So volume of this water is different and volume of this water is different. So this volume of this bucket is suppose like 10 liters, and the volume of this mug may be 2 liters. So the volume is changing. But like if you take this amount of water by a mug, then the volume of this water, volume of the water in the bucket and the volume of the mug is different. Here 2 liter and 4 liter. So it depends on the quantity. So that type of properties are called uh, extensive properties. Like volume, if we say enthalpy, gives free energy, internal energy, all comes in extensive properties. Next, we'll study the intensive properties. The property which do not depend the quantity of matter present in the systems. So extensive property do not depend the quantity of matter. So the property which do not depend the quantity of matter present in the system. So that property is called intensive properties. If you share the examples like temperature, pressure, refractive index, we can search concentration like molarity, molality, normality, mole fractions, etc. So like this, suppose you are in the outside, then the temperature is 25 degrees centigrade. So you are in outside temperature is 25 degrees centigrade, and when you come to the room, then also temperature is 25 degrees centigrade. So the getting the temperature both outside and inside, temperature remaining same, so it do not depend on the where you are. So that is extensive intensive properties. Or we can say, suppose this is the bucket of water. Let's say this is bucket of water. I mix with the sugar. So this is sugar solution. And if you take little amount of sugar from here, so little amount of sugar I will take from here in a mug. So here, so this taste of sugar, in mug, and taste of sugar in bucket is same. So if you taste the sugar in which is in bucket, and at the same time you take the small amount of sugar from the bucket by mug, and you taste both the sugar solutions in bucket and mug, then the taste will be remain same, because the concentrations, if you take the concentrations from bucket in a little, then also the concentrations remain concentrations in both bucket and mug will remain same. So concentration is not changing. So this is a type of intensive properties. So like that, pressure, refractive index, molality, all these things are comes under intensive properties. But how we will understand whether this is intensive or not theoretically? So how can you say that the ratio between two extensive property, the ratio between two extensive property is intensive. So in exam we can understand that whether this is intensive or extensive. How can do? Just ratio, take the ratio of two extensive property. If the ratio of two extensive property is intensive, then that is intensive. Suppose you say the molarity. So molarity is number of moles, volume in liter. So this is extensive properties, and volume also extensive properties. Number of moles extensive, volume also extensive, and these two if you divide, then that is intensive. So the uh, if two are extensive, then that the result is always intensive. So just take the if the both are the ratio of both are extensive, then the value of the ratio is always intensive property. So in this way we can identify whether the given property is extensive or intensive. We can identify by taking the ratios. So if the two values are extensive, then the ratio will be always intensive properties. And next we will going to study that that is state functions or state variable. So what is state functions? It is the thermodynamic state which only depends the initial and final condition of the state is called state functions. So a state functions is a thermodynamic states which depends only the initial and final condition of the states. So that says the examples are all thermodynamic quantity except heat and work. So if you says P, B, T, enthalpy, use free energy, all are state functions. So except uh, heat and work, so all are considered as state functions. Suppose if I say this PV curve, these two functions. So here this is P1, B1, and this is P2, B2. So if you go by here or by here or by here or by here, the delta P change in pressure is always P2 minus P1. So it, whether you go by this path, whether you go by this path, whether you go by this path, whether you go by this, any of these four paths, the delta P is always P2 by P1. So it do not depend on the path which it follows. It only depends on the initial and final state of the this variables. So it do not depend on the path. So this, like temperature also, if it says suppose PB T1 and T2, then it always T2 minus T1. It do not depend on this for all, like for path 1 this, for path 2 also this, path 3, for path 3 also this. So this is always remains same. So it do not depend on the path. So any path if you follow, the delta T is always T2 by T1. So it only depend on the initial and final state, and it do not depend on the path it follows. So this type of thermodynamic quantities are called path functions, state functions. And path functions are path function or path variable are what? The thermodynamic quantity which defines the path it follows. So like if he says PV car, then from here to here going, then if I here or here or here, so for like Q and for here, so this is P2, B2, so if you go by this, So for all these things, this is q1, this is q2, this is q3, this is q4. So by going from this path to this path, the q will be different. The q1 is not equal to q2, not equal to q3, because it depends on the path which it follows. So similarly w, so this w, q and w's are path functions, so it depends on the path which it follows. So after sometimes we will discuss the details about of the how our path, how the q and w depend on path, and why it is not a state functions, that we will discuss after sometimes. For time being, you are just now understanding the terms which you used repeatedly in these chapters. So next we will study the reversible and irreversible process. So first, reversible process. So what is the reversible process? So suppose if I take this, okay, and suppose this amount of water is there, or not water, suppose this amount of gas is there. Okay, and this is I have given the piston. Or you can say I'll just erase this. This is the piston. So suppose I give a small, this is very small, very my very small size stone I give. Then what happened? So the P external, previously that here P external was there, and also P internal is there. That's why this is in equilibrium. This state, this is stopped. The piston has stopped here, means P external equal to P internal. That is P external and P internal are in equilibrium. So whenever I added a small stones here, then what happened? The P external is increases. So P external equal to P internal plus this delta P. So very small. So this delta P is very small. So very small amount of P external is increased. So what happened? Since B external is greater than P internal, then the pistons move down. So what happened? This will So since P external is greater than P internal, so the equilibrium is disturbed because P external is greater than P internal by dP. So these pistons will move little down, little down. So suppose after let's say P external dash, and after that when the piston moves down, then volume is decreases, and you know volume is indirectly proportional, so pressure is indirectly proportional to volume, and if volume is decreasing, then pressure will increases. So after the pistons moves little down, the volume is decreases, then the pressure, then the volume will increases. So after that P external becomes this. After adding the dP, then P internal also become that, and the piston will stop. So again P external dash and P internal dash are in equilibrium. If piston has stopped means they are in equilibrium. So since volume is decreases, then pressure is increases. So internal uh, pressure is increases, and it comes to such that it is equal to P external dash. So again it will stop. Now what I will do, again one more stone I will add. Then what happened, this again this, again the pistons has moved little down, and now two small stones I added. So that then when I add one more stones here, then again the P externals become more than P dash external become more than P internal, that is P dash external equal to P dash internal plus dP, means again the volume will decreases, and again the pressure will increases. So this is become this piston will move down, and after that again the pressure increases, and again suppose P dash external equal to P dash internal. So what basically you are doing that, if you are adding the small stones, then little like piston is moving, and the P external is changing. Initially this was P external this amount. When I add small stones here, then this P external is greater than P internal by dP, and not that this dP is very small. So that actually this is nearly equal to P external, nearly equal to P internal, because dP is very small but little large. That's why that pistons has moved little. So when it will move, then the volume is decreases, and to decrease to counterbalance the decrease of volumes, the pressure will increases. So P internal again become to P external when the volume has decreases. So here the volume has decreases, so P internal is increases, because volume decreases means volume pressure will increases. So again the P internals become equal to P external, and again you add one more stones, then again the P external is greater than P internal. So again the what existing force is high, so again the volume will decreases, then again P external P internal will increases, because pressure is indirectly proportional to volume. So what happened, like here the P external is continuously changing, so that is not equal to constant, I can write. And since the P is very small. So what we are doing, that P external nearly equal to P internal, and that is equal to P of gas. So since in the whole process, what happened, that uh, whenever you are increasing the little amount of uh, uh, stones you are adding, then P external is becoming more than P internal. That's why the piston is moving downwards. So volume is decreasing, and since volume and pressures are indirectly proportional, so when volume is decreasing, then pressure is increasing. So again, the P internal of the or the pressure of the gas counterbalancing the increase of the P external, that is P external equal to P internal, and again they are coming in equilibrium, and again you are adding one more stones. Then what happened, again the P external is greater than P internal, so again the piston is moving downwards, and since volume has decreases, then that will increase the pressure. So again the P internals is going to equal with P external, and the piston will stop there. So again if we add one more stones, then again the P external is greater than P internal. So again the piston will move down. Since piston is moving down, then volume is decreasing, and pressure and volumes are indirectly proportionality. So if volume is decreasing, then pressure is increased. So if pressure is increases, then the P internal is increases, and that P internal again become equal to P external, and the piston has stopped. And again if you add one more stones like this, then again the P external is greater than P internal. Again the piston will move down, and since volume is decreases, then pressure of the gas will increases. So this pressure of the gas again equal to P external, and the piston will stops. So this continuous is occurs if you are adding the small piston. So for this whole process, the P external is changing from steps to step, because it is happening in a number of binary steps. So number of binary steps, the P external is changing. So P external is not constant. And since the very small amount of stone you are adding, very small size stone, so the P external is actually nearly equal to P internal. P external is greater than P internal, but very small. That's why sometimes we say that P external equal to P internal equal to P gas. So whenever you are writing the reversible reactions, and that on that time you will see that uh, work done in a reversible process, that P external is not taken as constant, and it is equal to P of gas. So whenever we are deriving the equations for work in a reversible process, on that times we again study that P external is not constant, and on that time we are studying that P external equal to P gas, because P external is nearly equal to P internal, and P internal is actually P gas. And since P external is changing in the whole process, so P external is not constant. So what happened, this is happening in a infinite steps to complete the reactions, to complete the process, and it is very slow process. And every time equilibrium is achieved, or every steps, I can say at every step equilibrium exists. And here the driving force is adding up stones, so the decreasing of volume is the driving force. So driving force is very driving force is very less. I can say driving force is greater than opposing force, but very less higher than opposing force. Means driving force is little higher than opposing force. So that's I can write driving force is higher than opposing force by a very small magnitude. Okay, and for irreversible process, we study the irreversible process. What happened here? Suppose this is the gas. So piston is here. So what happened? I add the bigger stones. This amount of stones I add at one time. Then what happened? So P external was there previously and P internal was there. So since P external equal to P internal was same, that's why the piston has stopped here. Here piston has stopped because P external equal to P internal. Piston stop because P external equal to P internal. But whenever I add a big stone, this is, let's say, big stone, whenever I add, then what happened, that pistons has moved so in a single step it has moved from here to here. So because by add, so here what happened, that P external equal to P internal by a delta P. So a bigger stone I added, so delta P means this is comparable amount of P changes. So what happened? So the pistons has moved from here to here by a single step. So if here the volume is decreases, and we know that PB is inversely proportional to volume. So if volume is decreases, then pressure will increases. So this is the initially. Then what happened after you add the stone? After stone added, then P dash external equal to again P dash internal, because if volume has decreases, so pressure has increases, so it counterbalance the, and this pressure of the gas again become equal to P external, because volume has decreased, then pressure is increases, right? So again this become equal, and again the piston has stopped because P external and P internal equal, and they are in equilibrium. So what I say is, in irreversible process, P external is not, P external is constant. Because because piston shifted one time only. So whenever this to here, only one time the pressure has changed. So from this to this, P external remain constant. So that's why I say that in irreversible process, P external is constant because it happens in a single step. So since whereas for reversible process, it is happening an infinite number of steps. So means each step P external is changing. So each step P external is becoming more and more. Right. This suppose at initial this is 2 atm, then again it will come and this will become 2.1, and again it will become 2.2, and again it become 2.3. So P external is changing. But for irreversible process, suppose you given that initially it is 2 atm, suppose you add the 5 atm, then it become like 5 atm, then it is decreases, it means single step it become only 5 atm only. So P external is remain constant. So in irreversible process, P external is constant because piston shifted one time only. So if you see that in this irreversible process, it occurs at single step. So single steps to complete the process, and equilibrium exists only at initial state and final state only, because no intermediate is there. So there is no questions of equilibrium will exist at intermediate states. And what happened here, this is very fast space, so process occur very fast process. And here what the driving force is decreasing of volume, and it is very much higher than opposing force. So driving force is very high value than opposing force. Okay. So next we will study the type of process. So type of process, one is isothermal process. Isothermal process. So the process in which the temperature remain constant, that is delta T equal to 0. So in Boyle's law, what we know, that T Boyle's law at constant temperature, but P is indirectly proportional to volume. So what happened, that is at temperature is constant. So at constant temperature, so what if we do the PV curve, then the isothermal is what? So if volume increases, then pressure will decreases because inversely relationship between them. So this will be like this. So As the volume increases, pressure is decreasing. And next process is isobaric process. In the process which occurs at constant pressure, that is delta P equal to 0. So what is the PV curve? So isobaric means pressure is constant, right? And next process is isochoric process, means the process which occurs at constant volume, that is delta V equal to 0. So if we say PV curve, then since volume is constant, so curve will that, because B is constant. And for process we can say, so adiabatic process, what the process in which no heat can flow into or out of systems. So in PV curve we can say this is nearly a watt of how isothermic, so this is little bit more so the slope is more slight than the isothermal. So if I do the combined PV curve, then I search for isothermal, it will like this, and for this is for isothermal, and adiabatic, this will be little bit more slight, this is adiabatic. And for isochoric means B constant, means this is isochoric. And which I take, okay. And for isobaric means P constant, this is for isobaric, so P is not changing. So this is the combined for all the process. So last process we can say cyclic process. So cyclic process, the state of a system we can define as the process of a state at a given state, the process you can define the process of at a given state which can occurs by different process, but at final at final but at final time it will returns to the initial state. Then the overall process is called cyclic process. So what is said that the process at a given state which can occur by a different process, but at the final time it will returns to the initial state where it was, the where it started. Then the overall process is called cyclic process. So example, if it says that all state functions what I said at cyclic process all state functions are 0. Like if a state function that is all at cyclic process all change in state functions are 0. Suppose if we say state function is temperature, volume, pressure, these all are state functions. So if a cyclic process, this is depend on cyclic process. So cyclic process, the change that is dt is equal to 0. Cyclic process of dp equal to 0. Cyclic process of dv equal to 0. So at cyclic process all change in state functions are 0. Okay, thank you.